All right, yeah, so that's right. 32 times 31, which is equal to twice times 2 to the fourth times 31. It's equivalent condition for being perfect. So yes, that's right. It's kind of neat how this geometric series ends up like generating the 31 here and making and helping make it perfect. So yeah, that's just all there is to this. Not much more. Greatest common factor, least common multiple. Now these are more important as we get into higher contests as well. So greatest common factor of two numbers. Well, how do you find it? It's the biggest factor that it's the biggest factor of both numbers. Biggest number dividing both of them. Well, we have to take the minimum prime power of all the numbers for each prime and take that as the power of the prime in the GCF, greatest common factor, and then you multiply all those minimum prime powers together. Now, why is this true? Why is this the biggest common factor? If you think about it, if we pick anything larger for each prime power, there will be some number that it doesn't divide, so no longer be a factor. If we picked anything smaller, we're missing out. It's not optimal, and there would always be a bigger factor because we can add another power to the prime. So we just take like the min of like the exponents for all the numbers for each prime, and then we multiply those prime powers all together to get GCF. By similar reasoning, the least common multiple is like the largest number or the smallest number, such that all of like the numbers you're calculating the least common multiple of divided. You want to take the maximum of all the exponents because that will like guarantee that your number is small and divides them all, since if it was any bigger, it would not be optimal. If it was any smaller, there would be one of the numbers that it's not a multiple of. And notice that for like if you have two numbers, like I don't know, some simplistic example, 12 and 18, uh GCF would be 2 times 3, right? We take the minimum of the powers in 2, which is 1. Same thing for 3, also 1. Whereas the LCM would be 2 squared times 3 squared. Indeed, we verify that 6 is the largest common factor of both of them. 36 is the least common multiple of both of them. If we multiply them together, what happens? 2 cubed times 3 cubed. But notice that this is also what we get when you multiply these two. Now, this is not a coincidence, of course. This is because in two numbers, if one of them is the maximum, the other is the minimum. If one of them is the minimum, the other is the maximum. So the LCM will always, the GCF will always pick one of the exponents. The LCM always picks the other. If you multiply them, you'll get the product of the numbers. So this is a useful property, especially for like equations involving GCDs and LCMs, that the GCD and LCM multiplies to the product of the two numbers. If two numbers have the greatest common factor of 1, they're relatively prime. They don't really share any factors other than 1. And yes, we'll talk about more about like this GCF LCM stuff maybe in the next slide. So calculate the GCF of 15 and 45 as well as 36 and 54. Calculate the LCM of 24 and 40 as well as 10 and 12. And what's the LCM of 14, 35, and 6? We're throwing in 3 numbers here for that one. And let me just say that while GCF times LCM is only necessarily the product of all the numbers for 2-digit, the method to find them generalizes to any amount of numbers you have. All right. Okay, now you can chat me your answers when you're done. All right, so I'm seeing a lot of good answers. 15 and 45. If you want to find the GCF, you can eyeball that 15 divides both. So 15 is the GCF. 36, 54, 3 times 18, 2 times 18. LCM of 24 and 40. 8 times, that would be what? 8 times 3, 8 times 5. So it'd be 8 times 3 times 5, which is like 120. 10 and 12, this would be 60. 14, 35, and 6. 2 times 7, 5 times 7, 2 times 3. So 2 times 3 times 5 times 7 would be like 210. So these are just, if you get good at this, you can just eyeball these yourself without even having to list out the prime factorization. But just for the sake of it, we're going to do it that way too, since that's the best way. 3 times 5 is 15's prime factorizations. 3 squared times 5 is 45. GCF takes the minimum exponents of each. 3 to the 1, 5 to the 1 is 15. 36, 2 squared times 3 squared, 54. 2 times 3 cubed. Now, GCF of these, take the minimum exponent of 2 to the 1, minimum exponent of 3, 3 to the power of 2, 18. LCM of 24 and 40. Well, maximum exponents each, 2 cubed times 3, 2 cubed times 5. We take maximum exponents of 2, 2 cubed, maximum exponents of 3, 3 to 1, maximum exponent of 5. That's 2 cubed times 15, 8 times 15, 120. 10, 2 times 5. This 12, 2 squared times 3, 2 squared times 3 times 5. That's 60, 4 times 15. This is 2 times 7, 5 times 7, 2 times 3. Maximum power of 2, 2. Maximum power of 3, 3. Maximum power of 5, 1. Or 5 is the number that has a maximum power of 7. Maximum power of 7 is 7 and 1. 2 times 2 times 5, 7 times 7 is 210. So yeah, of course, like the method to find GCF and LCM generalizes to any amount of numbers. Okay. So now we have some more factor tricks. You can use a Venn diagram to calculate the GCF and LCM of numbers, listing the prime factorization of each number. Put the common ones in an overlapping area. The product of the numbers is the GCF, and the product of every number in the diagram is LCM. This is more useful for GCF of 3 than 2 numbers. You can just list the factors. You can see how this works on the top right? You can also use this to see why the product of GCF and LCM of 2 numbers is a product of both. If you look on the bottom right, the product of 84 and 140 is 3 times 2 times 2 times 7 times 2 times 2 times 7 times 5. So the LCM would be all of this stuff right here. The GCF would just be this circle 2 times 2 times 7. The product counts this part twice and these parts once, which is exactly what you get when you multiply the LCM and GCF. So this is an easy, like interesting way of visualizing it, I'd say. So for this example up here, we have that like 2 times 3 is the common factor of all of them. Although really this is just constructed by finding the prime factorization in the first place. Well, I guess it is kind of a bookkeeping device for it. So the LCM would be 2 times 2 times all of this stuff multiplied together, which would be 2 to the 4 times 3 squared times 5. If you check the prime factorizations, this is 2 to the 4 times 3 is 48. 3 squared comes from 36, and 5 comes from 90. This is right. GCF is like this intersection of all the 3 circles, 6, which surprisingly small, but it's correct. So now we'll have you use the Venn diagram to find the GCF and LCM of 45 and 105. All right, so our meeting time is running out, but anyways, quickly the LCM, JCF 15 and 315. Sorry, draw a better Venn diagram than this. Here we have 105, we have 7, 3 times 5, and a 3 here. So the LCM would, the GCF would be this, which is 15. The LCM would be 3 times 3 times 5 times 7, which is 9 times 35, which is 315. And yeah, that's just how you use the Venn diagram. Comes pretty naturally, I guess. But yeah, using prime factorization is still probably the best and most reliable way if you don't have time to just draw this out. All right, so it looks like our free meeting is over, so I will end and rejoin.